Ahoy! Welcome back to A View from Earth, brought to you by the Fiske Planetarium at CU Boulder. We hope you're all doing well and staying safe. As with the rest of the university and many public spaces around the world, Fiske's theater is closed to the public for the foreseeable future due to the COVID-19 pandemic. However, we are still so committed and excited to bring astronomy and education to you that we've started a whole host of free online offerings so that we can stay connected and keep bringing you the Fiske content that you know and love. Plus, some new stuff like this podcast. So, thanks for tuning in and learning with us here today. My name is Colin Sinclair. I am a CU student and a presenter at the Fiske Planetarium, obviously one of the co-hosts of this podcast, and I'm here today with Tara.
Hello, I'm Tara Tomlinson. I'm a planetary scientist, a CU alum, and also a presenter here at Fiske Planetarium, as well as the outreach coordinator for all of our community outreach efforts.
So, we've kicked off the series with some pretty exciting topics, black holes and Mars. But this week we're going to talk about something that often gets less media attention, but is no less interesting to the curious mind, the outer solar system. As you likely know, our solar system is composed of a star, the Sun, 4 rocky planets, 4 giant or Jovian planets, and many smaller comets and asteroids. Some of these smaller bodies lie in the Kuiper Belt, a region of the solar system that exists beyond Neptune. It is home to hundreds of thousands of icy bodies, and of course, America's favorite dwarf planet, Pluto. This region is the topic for today's episode. In the following interviews, we'll learn about the New Horizons mission with Dr. Fran Bagenal and what it takes to send spacecraft to the far reaches of the solar system. We'll also talk with Ryder Strauss about something called occultation and how astronomers can use them to learn about comets that are incredibly far away, all from our own backyards. But first, the news.
All right, so joining us again this week is our news correspondent, Rami, with a story for us about comets from the outer solar system.
Yes. Hi. Hello, Tara. Hello, Colin. It's me, Rami. I am also a presenter at Fiske Planetarium, but today I will bring you the news. So on June 15th, the Solar and Heliospheric Observatory detected its 4,000th comet. Hooray! So SOHO was built to study the sun. As is often the case, though, observatories are multi-talented. In the case of SOHO, what was built to stare down the sun can also be used to find evidence of comets. So for anyone not up to speed, comets are small, icy bodies from the outer solar system that swing in close by from time to time. When they get closer to the sun, that ice starts to melt, leaving these gorgeous tails that we associate with comets. We really like comets because instead of having to send spacecraft all the way out there past our furthest planets and dwarf planets, they come to us. So we can learn a lot about what's way out there, and we don't have to go particularly far to do it. In fact, despite comets spending much of their time extremely far away, some of these comets come in extremely close to the sun, even closer than the orbit of Mercury. And these are called sun-grazing comets. And they're easily spotted by an observatory pointed right at the sun. So all they have to do is take a look around and find any comets passing through. So while SOHO was built to study the sun, it does have a neat side effect of being able to find things near the sun, like these comets. However, scientists are generally caught up with the sun, so they rely on amateur astronomers to spot the comets in the data. About 95% of the comets found by SOHO were actually spotted by amateurs, including comet number 4000. So if you're interested in amateur astronomy and have some time on your hands, maybe you can find comet number 5000.
So we should probably go ahead and throw a disclaimer out here that yes, you should look for comets close to the sun, but please, God, don't stare directly at the sun.
Please don't stare at the sun.
That's not going to
Unless you are a telescope built for the sun.
My telescope manual has literally on every single page on the bottom, it says, do not use this telescope to look at the sun. It will cause permanent eye damage. Every single page. So
they just want to make sure you really got it.
Hey, Rami, thanks so much for doing the news. We really appreciate you putting together these segments for us.
And I appreciate you having me here to give these segments.
Ryder Strauss is a recent graduate of CU Boulder and is a project lead for RECON, the Research and Education Collaborative Occultation Network. He uses small backyard telescopes to observe tiny objects like asteroids at the far ends of the solar system, using a technique called occultation, with each occultation only lasting a fraction of a second. How much can we learn about these faraway objects that we can't see? Turns out, quite a lot. Ryder, thanks for being with us today.
Yeah, thanks for having me.
So first off, tell us a bit about Recon and how you got involved.
Oh, so how did I get involved? It was actually a little bit of a not necessarily an accident, but close to an accident. I wasn't seeking out this particular field of research or this particular position. I didn't know John Keller. I wasn't particularly involved at the Fiske Planetarium level. I was a sophomore trying to get my foot in the door a little bit on some kind of. I needed job. I needed money, and if I was going to get a job, I wanted it to be involved in research, so I could get my foot in the door in that area. And so I went onto the APS Research Employment Opportunities page, and there were a couple of job listings there. One of them was from Nick Schneider on the Maven project, and one of them was with John Keller on the Recon project. It's funny how the universe sort of works out sometimes and puts you right where you're supposed to be. This was between the two jobs, Recon was my second choice at first. I was especially excited about the Maven position, and this had a little bit more focus on the sort of education outreach side of things, which I hadn't had a whole lot of exposure to. But after getting involved with the project, it's grown to be a really, really huge part of my life and huge part of what made my undergrad experience, my experience at CU, so awesome, and informed what I'm interested in doing moving forward with my research and forward into grad school at Northern Arizona University, where I'll be heading in the fall.
Mm-hmm. Tell us about Recon, the mission, and what it is, and what you're doing with it.
So Recon is a fancy NASA acronym. It stands for the Research and Education Collaborative Occultation Network, and what it is it's essentially made up of a whole bunch of teams of volunteer citizen scientists, mostly at local high schools and middle schools and a couple of local universities, all the way up and down the sort of western side of the United States, from I guess we now have some sites in Canada, and all the way down to southern Arizona. And we've supplied each of these teams with a backyard 11-inch telescope and camera equipment to sort of form a picket fence or fishing trawl across the western United States to capture what's called an occultation. And an occultation is basically when a small object passes in front of a distant star, it casts a shadow of that starlight onto the face of the Earth. And if you're within that shadow, observing the star at the time of the occultation, you'll see that star blink out. And if you have enough sites within the shadow, you can measure the timing of that blink. And if you fold the timing of that blink in with the geometry of where your site is on the Earth, you can draw a picture of that shadow that you found yourself under. And because stars are super far away, the starlight is all sort of coming in perfectly parallel. So as it turns out, the shape of the shadow forms essentially a perfect image of the shape of the object in the plane of the sky. And so we've got this big old network of citizen scientists that all go out on predetermined nights to record, plus or minus 5 or 10 minutes about the predicted nominal time of when one of these events is predicted to occur. And they'll all record the videos and see if they actually see a dip. And when you see a dip, it's super exciting because you can get these really, really high resolution, high precision measurements of these objects that are so small and so far away that you just can't get this kind of detail on them with more traditional observational techniques.
So my understanding is that you are looking for occultations that are caused by trans-Neptunian objects, right, or TNOs. Can you tell us a bit about TNOs and why they are important to study and understand?
Yeah. So the term trans-Neptunian object, in its sort of explicit definition, it means an object that passes across Neptune's orbit at some point in its lifetime. In our sort of recon world, we use the term TNOs as sort of a general term for outer solar system object, even though they might not strictly match the definition of a trans-Neptunian object. But the interesting part about the interesting thing about these objects in the outer solar system is that because it's so distant and so cold and things are so sparse out there, these objects haven't had very much opportunity to sort of interact with each other. And they're far from the sun. There was a lot less sort of interplanetary dust during the formation. So it wasn't the sort of violent, chaotic, super active type of region that the inner solar system, when the inner planets were forming. And because of this, these objects, many of them exist much as we expect they would have been 4 billion years ago when they first formed in the during the infant years of the solar system. And so in studying these objects that are about as primordial and as old as they come in the solar system, we can learn about the physical properties of the makeup and structure of the solar system when it was forming.
Yeah, that actually leads in perfectly to our next question, which is just kind of, what is the overall goal of recon? Basically, you're doing all these observations. Are you guys like making a catalog, or are these actually being used to study these objects further? What's going on there?
Yeah, so the overall goal of recon is to study and understand the physical composition and makeup of these individual objects. Lots of other there are lots of other surveys that study the outer solar system. But many of them study it sort of more as a bulk population. They study, the overall structure of the outer solar system and the sort of dynamics of it. And we're slightly more interested in the sort of physical makeup of these objects. What are they made of? What are they shaped like? How shiny are they? How dense and massive are they? And so everything we are trying to do with recon is trying to answer those questions, essentially.
Okay, so you're getting like into the nitty gritty rather than sort of a big picture sort of thing.
Yeah, it's a very, very object by object effort, and that's actually an interesting sort of strength and weakness of recon. Is the outer solar system is hard to study, even by occultation. It's really hard to study because when you get these, you need to get a prediction of when an object is going to pass in front of a star. And so you need to know where the object is in the sky and what direction it's heading, so you can predict sort of what its trajectory is. And to do that, you need observations with really big telescopes. And you take these observations with these really big telescopes, and you get a sort of physical, what's called an astrometric measurement of where the object is in the sky. These feed into the predictions. These astrometric measurements are really easy to obtain for, say, main belt asteroids. So asteroids in the asteroid belt and near Earth objects. Those objects are very bright and they're very easy to observe with even a smaller telescope. Trans-Neptunian objects are very hard to observe. You need a very big telescope with a lot of light collecting area because they are super duper dim. And you need to take really long exposures again, so you can collect as much light as possible. And because they're so far away, just because of the way the geometry works out, you have some given angular uncertainty in the position of the object in the sky. And for an object that's closer to us, a 1 degree angular uncertainty corresponds to a much smaller distance than an object that's way far away from us. And so because of those two factors, you have these really large uncertainties on the position of the object, and therefore you have really large uncertainties on the position of where that shadow is going to fall on the face of the Earth. So because we have these really high uncertainties, we need to space, even though we've got a huge network of a bunch of telescopes, there's like 55 telescopes, we need to space them pretty far apart so we can cover a really wide uncertainty region on the surface of the Earth. And because of this, if we get a detection, these telescope sites are spaced really far apart. And so it's very rare for us to get sort of really high resolution, high spatial resolution on the profiles of these objects. Typically, we'll have 1 or 2 or 3 detections, which can give us some constraints as to, is this object obviously really non-circular, or is it probably pretty circular? Is this object really big or really small? These sort of broad measurements. The important thing with an occultation is these astrometric measurements that I was mentioning with the big telescopes. When you observe an occultation, even with just one sight, you know for sure that at that moment, the object was at exactly the same place in the sky as that star. And because of the Gaia satellite and the Gaia catalog, we know the positions of these stars to a really high uncertainty. And so that occultation detection provides an incredibly precise astrometric measurement of the position of an object. And these occultation measurements can be so precise in terms of astrometry that they can feed into other future better predictions for occultations. That's what happened with Arrakoth. Is there was occultation effort after occultation effort after occultation effort. And even though this is a very distant object in the trans-Neptunian population, for that final occultation campaign where you saw that they got enough resolution on the object to see that double lobe structure, that was because they had taken these measurements so many times before that the uncertainties on that shadow had really narrowed down, and they were able to send 20 or 40 telescopes and space them really tightly, 5 kilometers apart, to really get that high resolution. So that's the other thing that the sort of goal of recon is to provide these it's a gift that keeps on giving, a positive occultation detection, because if we can get with recon a really broad detection, we can think about going after sort of more focused, higher precision, more targeted occultations.
Yeah, I remember when the Arrakoth occultations were happening, and it was like, all right, so now we know that it's 30 meters across and shaped like a peanut, and then 2 months from now we'll know a little bit more, and then we'll find out more and more. And then by the time we got there, it was shocking to me how accurate the occultation represented the actual object. Like when we got there and took pictures of it, it looked just like the shadow did.
Yeah, it's really cool. Amazing.
And I think that would be, kind of one of the strengths of a program like Recon. Like you were saying, you have telescopes all up and down the West Coast. So, if San Francisco is rained out, you might have somebody in Portland that actually got the occultation, or vice versa, or what have you. So it seems like having this whole network online really beefs up your chances of getting really good data.
Yeah. It can sometimes be unfortunate when it's super duper clear in southern Arizona, because of course it is, and obviously in Seattle it's rainy, and if the occultation shadow falls over Seattle, then we're out of luck. Looking through our positive detections that we've had, the vast majority of them have been detected from sort of southern Oregon, northern Nevada, southwards. And I noticed this, and I thought this was interesting. For a split second, I thought, oh, that's weird. That seems like a surprising bias. And then I realized, oh, that's because that's the part of the network that actually has clear skies. So if a shadow passes over the northern part of the network, we're less likely to actually observe it. So shout out to the observers up in Washington and in Oregon for being troopers and getting out there and observing whenever you can. I know the weather is problematic, and in the winter, I think sometimes those observers up north get frustrated with the observers down in Southern California, their wonderful 70-degree nights.
All right. Well, Ryder, thanks again for joining us. It's been a pleasure to have you and learn all about recon and kind of what you're doing.
Yeah, thanks for entertaining my long-winded answers to your questions.
No, it's all right. You know, that's why we ask them, is to kind of hear all about your thoughts. So.
Hey everybody, so today we are talking with Dr. Fran Bagenal. Dr. Bagenal is a Professor Emeritus at CU Boulder and has been involved in a number of planetary science missions from Juno to New Horizons, Cassini, Galileo, Voyager. She's sat on or chaired a growing number of NASA assessment groups, advisory councils, review boards, and has received numerous awards for excellence in research and teaching. Dr. Bagenal is also a longtime proponent of a mission to Pluto, and her work as co-investigator for the New Horizons mission makes her a prime resource for understanding the environment of the Kuiper Belt and beyond. And her enthusiasm for teaching and lecturing is legendary, and she may be the only CU APS faculty with an IMDB page. So we are thrilled to have Dr. Fran Bagenal here with us today. Thanks for joining us, Dr. Bagenal.
It's a pleasure. Great fun.
We're happy.
Hopefully we'll be back in person in Fiske before too long.
Fingers crossed. All right, so let's kind of jump right in. So we're here today to talk about New Horizons and the outer solar system and some of the cool stuff that's happening out there. So I figured we kind of start at the beginning. Talking about New Horizons, it was accepted by NASA in 2001, launched in 2006. But you and some others had been pushing for a mission to Pluto for a while before then. Is that right?
Yeah, it all really started back in 1989 when I just started at CU. And we had the Voyager flyby of Triton at Neptune. And this got everybody excited about Triton is a captured object at Neptune and thought to be a Kuiper Belt object. But of course, back then, we didn't know about the Kuiper Belt. All we knew is that Triton was probably captured. It was going the wrong way around Neptune. And that it kind of the same size as Pluto. So there was some interest, you know, what do we do now after Voyager? Help, panic, where do we go? What do we do? And Alan Stern came to me, he was a graduate student at the time, and said, let's go to Pluto. And I thought, you know, who cares about Pluto? Piddly little object, who cares? You know, because I deal with big objects like Jupiter, Saturn, all these things. And so he persuaded me, though, that it would be an interesting place to go, because in some ways and we'll come back to this, I'm sure, you can think of Pluto as a very large comet, if you like, in that it likely hasn't. We know it has an atmosphere. We knew back then it had an atmosphere, and the atmosphere is probably escaping. So you can think of it a bit like a comet. So that's what got me interested in it scientifically. But what's really interesting is this. When we started 1989, there was no Kuiper Belt, just Pluto. And then in 92, they discovered the first Kuiper Belt object. And then many, many more that were discovered quite quickly using Earth-based telescopes, looking out there and seeing these little dots. And we realized that there was another zone out there in the solar system that had not been explored. And this became very important in terms of solar system formation. So the key to us successfully getting NASA interested was very much the idea that Pluto was one of the Kuiper Belt. And so before we discovered the Kuiper Belt in the mid-90s, you know, we were just wasting our time. People were like, who cares, who cares? So there was a combination of what to do next and scientific motivation for going, but also the discovery of the Kuiper Belt to be.
Well, it certainly does feel much more familiar than I think a lot of people might expect when we talk about Pluto. You see stuff that kind of looks earthly, and you're like, wow, it does. That feels very real, and it's very striking to look at. So talking about, you know, these unexpected kind of phenomenon that we observed when we got to Pluto, there's probably tons of surprises when you start looking through the data from New Horizons. Was one of them your favorite, or one that you think was most surprising, one fact that we kind of learned from this mission?
I think the glacier and this thing here, the glacier here, you're seeing nitrogen ice convecting, turning over. Now it's geological timescale, so it's 500,000 years to turn over. It's not rapid. On the other hand, it turns out that nitrogen ice is less viscous or more runny, flows more easily than water ice. And so you can have these glaciers and this convection turning over of nitrogen ice driven quite easily with very little heat from below. And then that leads to a lot of geological activity, which was, I think, a big surprise. Yeah.
So when you say the fluidity of ice, you just described ice as being viscous or not viscous. How does that work? Because when I think of ice, I think of a solid, right? That's the solid phase of water, for example. So what does that mean, the fluidity of ice?
There's two ways of thinking of it. One is just to think about glaciers, which move fairly slowly. I mean, glacial comes from the idea of a glacier moving slowly, and the ice moves. But if you go and you look online and find Balog's movies of the glacier, it's really amazing. He has these time-lapse movies of the Earth's glaciers and pointing out their retreat, but you can see the flow. A better way of thinking of it is to use what I do when I teach this in planetary classes, is to take silly putty. And if you take silly putty and you warm it a bit in your hand, and you make a nice ball, and you put it down on a table and wait, you will see it flow out, okay? And that is low viscosity flow, right? And if you warm it up more, it'll flow quicker, right? You could say the same about jam or take your favorite food that slops around, I don't know, Jello or what are other foods that flow? I guess you could take honey, right?
The classic example of syrup, maybe.
Syrup is the other one, right? If you have it very, very cold, it moves very slowly, and then you warm it up a little bit, and whoa, it flows quite quickly. So the same is true for ices. They are not, and indeed rocks flow, right? When they warm up inside the Earth, they flow. So most of these things that you think of as being solid, if you leave them long enough, they will begin to flow. Yeah.
And of course, New Horizons didn't just stop at Pluto. It kept going. We had a rendezvous with Arrakoth, another small Kuiper Belt object, and New Horizons is still going out. So do we have any idea of where New Horizons is headed next?
Well, there is hope that we could do a flyby of another Kuiper Belt object, but you have to, it's tough out there. So to go from Pluto to Arrakoth, if you hold up your finger and you think from your eye to your finger, that angle is about 2 degrees, okay? Maybe it's 1 degree, maybe 2 fingers are 2 degrees. On that order, depending how long your arm is, of course. But the point is, we had very little maneuverability, about 2 degrees, when we were at Pluto to get to Arrakoth. Because of the fuel, if you want to change direction, you have to burn an engine on the spacecraft. and we didn't have a lot of fuel. We have even less now because we've gone past Arrakoth. And so there's very little fuel. So that means that you've got to look for an object that's right in that direction. And the chances of that are extremely slim. We're using Hubble Space Telescope and other ground-based telescopes to look and see if we can see anything out there, but I think the chances are slim. And so the idea is for the extended mission, the continuous, if we're able to keep continuing, is to do a variety of things. That is, look at Kuiper Belt objects from different directions to try and learn a little bit about them from there. I'll come back to that in a second. Another is to look at the background, Lyman alpha, of the far astronomical observations that you might want to take of the UV light that comes from the stars outside. We will measure the solar wind using the solar wind instrument, the SWAP instrument. Variety of tools of things that we can do, looking at different Kuiper Belt objects and looking at the solar wind, watching it slow down as we move out through the heliosphere, the sphere of influence of the sun, because the effect of the material outside coming in and slowing down the solar wind. So there are a variety of things that we're doing, but I think the most exciting one to me is actually something that came out been demonstrated in the past few weeks, is this citizen science experiment that is to look at Kuiper Belt objects from the viewpoint of not Earth looking out, but New Horizons, which is out there looking sideways, if you like. So a slightly different viewpoint. And so when you look at things from different viewpoints, you get to see the location, you get to work out where it is. It's called a parallax effect. And it's been used for centuries for measuring the distance to stars. And we can use the difference in viewpoint from Earth and from New Horizons to sort of work out where these objects are. It's a really cool experiment. And we've been engaging with citizen scientists to look for objects like that and do this experiment. And you can go online and see it. But maybe the coolest thing is that Brian May from the band Queen is involved. He's an astronomer and keen in these things. And of course, he's written music to go with it. And you can go online and see it. It's kind of cool.
That's very cool. I did just see an article where they had used that parallax technique to look at Alpha Proxima Centauri, the closest star.
Cool.
And they had been doing updated measurements on how far it is to our closest star, thanks to
our closest star. Yeah, right. Exactly. Really cool.
Yeah. So since we have learned so much from just this one flyby of Pluto and, out in the Kuiper Belt, is there maybe another Pluto mission that's, pardon the pun, but like on the horizon?
There is a mission, and there's a group of people who are pushing for that. And that would be interesting and a good thing to do. It would be challenging, because if you want to go into orbit around Pluto, you have to not only go all the way out there, but you also have to slow down to go into orbit, and that is tough. So you have to carry a fair amount of fuel to do that of some kind. I don't know. The other option is to say, well, why not go to one of the other Kuiper Belt objects and learn about that? Which is more important, to go back to Pluto or to go to a different Kuiper Belt object? For me personally, I think I would go with a different Kuiper Belt object. Alan Stern is pushing to go back, with some of his members of his team to Pluto. I think go elsewhere and go look at a different Kuiper Belt. I also really want to go look at Triton, which is the captured Kuiper Belt object in orbit around Neptune. Uranus and Neptune have only been explored by Voyager flying by, the only spacecraft that have gone close to them. And I think it would be very interesting to go to either Uranus or Neptune and explore those planets and find out what's going on. But their outer solar system is tough. It is difficult. So it takes time.
I know that's kind of a big debate that I've had with some of my teammates, is they think we should really go back and study this thing that we already visited because we know it's really cool and we know that it has a lot of potential. But then on the flip side, there's all this other stuff that we haven't been to yet that, I mean, personally, I agree. I think it's worth going and checking these out too.
So I'll just pick on Mars for a second. Tara, I hope you don't mind, but you know, we've been going back to Mars again and again and again and again. And yes, I know it's interesting, exciting, but we've done it. And we need to go somewhere that's a lot tougher. Venus, next door planet, right? Greenhouse gas that's gone absolutely crazy. An atmosphere that's like out of this world, right? Hot and an Earth that's gone extreme greenhouse global warming. I think we really need to go back and understand Venus. You know, get under the clouds, look around, go back up, cool off, go back down, have a look around, go back up, cool off, or whatever. I mean, I think there's 100 different things we could do at Venus that would be really interesting. So, and that's just a neighborhood, and it doesn't have a magnetic field. So I'm not pushing it for my own professional purposes.
So let's talk. We always like to kind of ask some of these, you know, kind of personal questions about you as Dr. Fran Bagenal. My first question in this category is, what advice do you have for a person who really wants to study the outer solar system and work on spacecraft missions? Imagine there's some young listener out there saying, man, this sounds like exactly what I want to do. What would you tell that person? How can they get to kind of do what you're doing?
Number one, stick with your math. Do your math homework. Just do your math homework. It's really important. And I, by the way, would justify the entire NASA budget on encouraging kids to do the math homework. Benefits are huge. Even if you don't go into space research, doing your math homework is important. Number two, yeah, stick with your science and be curious and follow your curiosity. But if you want to do planetary science, then you have to stay kind of multidisciplinary, right? Because planetary science, you find you've got a bit of geology, a bit of geophysics, a bit of atmospheric science, a little bit of ice science, a little bit of gas, a little bit of plasma, a little bit of magnetic fields. You have to sort of be very willing to and open-minded to learn a little bit about all these different things, because they all tend to come together when you look at a planet that has a bit of everything. It's a very multidisciplinary science. If you really, really, really want to focus in, then, you know, go and work on the atomic physics of some atom, right? And you don't think about the other areas, or you know, maybe molecular biology is pretty sort of narrow these days. I don't know. Maybe I should. You know, you have to find what you're really interested in. Astrophysicists like to look at huge distances, fairly limited amount of information, but they leap about with fairly limited amounts of information and wild imaginations and come up with all sorts of cool stuff. Planetary scientists are a little bit more down to earth. They want some numbers, they want an image, they want some data to constrain their thinking, but you have to be multidisciplinary. Wouldn't you say, Tara, wouldn't you say that's the case?
Yeah, absolutely. Planets are really complicated.
Yeah.
Like you said, they have atmospheres and magnetic fields and geology, and even like I'm just specializing in geology, but there's ice geology and rock geology and surface atmosphere interactions that you have to worry about, and there's a lot going on.
Just look behind me here, right? Look at this stuff here. Lots of stuff. So those are the words of advice. You know, persistence, of course, with everything. But do your math, be curious, and keep your mind open to a range of science.
It has been such a pleasure to talk with you, and it's so, every time we do one of these, I learn so much. So thanks very much for sharing.
Well, lovely to talk with you all. Happy to do this again anytime.
Thank you so much.
Great. Cool. See ya. Bye.
Thank you.
All right, folks, that's all for this week. Thank you again so much to our guest, Dr. Fran Bagenal, and to Ryder Strauss. If you guys want to hear the extended interviews for either of those are going to be available on our YouTube and SoundCloud. And of course, come back next week for sure. We're going to be talking about asteroids with Dr. Daniel Shiras, who has an asteroid named after him. He's kind of an expert. We're also going to talk to Kaya Sorley, who's going to tell us all about planetary defense and what we're doing to keep asteroids from hitting us here on the Earth. Our podcast is available on YouTube, SoundCloud, Spotify, and Apple Music. We also want to invite you guys to visit our website, www.colorado.edu/Fiske, where you can see a schedule of all the upcoming shows with guests and topics. There's also an option there for you to submit questions for our experts to answer on the air. So if you have any burning questions that you'd like to hear us answer, send us a message. You can use the website form or just email us at fiskepodcast@colorado.edu. So be sure to comment and subscribe to make sure you don't miss an episode. Hopefully we'll see you next week.